Hi guys, welcome to our second video in chapter 25. This video is going to cover section 25.2, which is all about radioactive decay. You can see our objectives are pretty short. We want to explain why certain nuclei are radioactive, and we want to be able to apply our knowledge of radioactive decay to write some balanced nuclear equations, similarly to how we would write chemical equations, but different in some ways. We do have a pretty long list of vocab words here, so we'll get into them. To start, a new vocab word for you, a nucleon. That is referring to any particle inside of a nucleus, and that is a proton or a neutron, right? Because they're in the nucleus, we call them nucleons, okay? Also, the strong nuclear force, our second vocab word. This is one of the four fundamental forces of the universe, and this is a force that acts only on subatomic particles that are very, very close together. So protons, neutrons, and even electrons when they get very, very close. And you can see for our four fundamental forces, those are gravity, electromagnetism, the strong force, which we're talking about, and weak force, which is similar to what we're talking about. And these are the four forces that exist in the entire universe, and they govern the laws of reality as we know it. And believe it or not, we actually do not have a very good understanding of any of these, but especially we don't really understand gravity or the strong force or the weak force. Electromagnetism, we have some better understanding of, but still not complete. So there is still quite a bit of research to be done on our universe in terms of explaining what exactly happens and why. All right. So to start, we talk about our strong nuclear force. This is the force that overcomes the electrostatic repulsion and allows protons to come together. Okay. Without the strong nuclear force, the protons would just push apart and they would not be able to form a nucleus. This force is not well understood. Okay. We just know that it exists because we have evidence of it being released with nuclear fission. And we know that something must be holding together those protons. So that's how we know this exists, though it is not well understood. Another poorly understood force is our weak force. This is actually the force that it plays a role in radioactive decay by like pushing out the radiation. But again, it's not well understood. We just know that it exists. Okay. If you want to learn more about these, then I recommend that you study nuclear chemistry in college. It's fascinating stuff to think that there are two forces that are fundamental to the universe that we basically don't understand very well at all. Interesting to find that kind of stuff. Okay, so I want to talk again about what makes our atom stable or not stable. So the stability of a nucleus relies on a balance between the electrostatic force and the strong nuclear force, or that force of repulsion between protons and the force that attracts them in with the strong nuclear force. Okay. And we can actually correlate this with the the neutron to proton ratio. I have a worked example here. You can pause the video and take a look on the right-hand side for how the neutron to proton ratio is calculated for something like lead. It's very simple. You calculate your number of neutrons by subtracting your atomic number from your atomic mass, and then you divide that number, your number of neutrons, by your number of protons, which is given as your atomic number, and that will give you some decimal. In the case of lead, 206, that decimal is 1.51. Now we find that for low atomic numbers, up to 20, like right all the way less than 20, the most stable nuclei have a 1-to-1 ratio. This is why carbon is carbon 12 for the most part, because it has 6 protons and 6 neutrons. Same with oxygen 16. It's going to have 8 protons and 8 neutrons. Larger elements have a steadily increasing neutron to proton ratio, where the largest atoms like lead, they actually have a ratio of 1.5 to 1. And if we go all the way up towards things like oganesson or even larger element, we're looking at almost a 2-to-1 ratio of neutrons to protons. So essentially, the more neutrons you have, the more protons you have, the more neutrons need to be put into that nucleus to kind of cushion them and make sure they can actually come together. So this graph actually shows us what's called the band of stability. That is the area in the graph where all stable nuclei are found. And we can see that this graph is made out of a graph of the number of protons on your x-axis and your number of neutrons on your y-axis. And we can see the bottom line that I'll highlight in green. That represents a 1-to-1 neutron to proton ratio. And then if we look at the purple line, that is showing us a 1.5 to 1 ratio. And you can see that the elements get closer to that 1.5 number as we get higher up. And then once we get over 1.5, elements do have more neutrons, but they're still not considered stable because they just don't last long enough to be found in nature. And so they're artificial elements. So they're not onto this band of stability. That's why we end at lead, just because that is the end of our naturally occurring elements for the most part. So we have some other types of radioactive decay that I think are worth talking about here. I want to go and make sure that we all are familiar with our alpha, beta, and gamma decay. Those are pretty straightforward. We've seen those, and we can see how they change our atomic numbers, or our atomic charge, which is Z. That's the number of protons. That's what Z stands for. But we have these two new radioactive decay types called positron and electron capture. So a positron emission, and that's kind of interesting. A positron is a positive electron. That's where it gets its name, positive electron. But a positron emission is a radioactive decay process that has the emission of a positron. Surprise, surprise. Well, a positron is a particle with the same mass of an electron, but has a positive charge. So it's interesting. It's actually an antimatter example, where if it were to combine with an electron, it would annihilate that electron and would be left with just a lot of energy. So that's a positron. And you can see that the positron actually, it is emitting a positive particle. So you're actually going to convert a proton into a neutron. And what happens is if you convert that proton into a neutron by getting rid of the positive charge, well, your number of protons in your nucleus will decrease by 1, right? But since a neutron and a proton have about the same mass, then your atomic mass will be unchanged, which is kind of cool. So now we can go down by 1 in our atomic mass. In a similar process, electron capture actually happens when a nucleus is able to draw in a surrounding electron. Obviously, it's usually going to be the closest one because that's the one that's closest and easiest to hit it. Now, this electron combines with a proton and forms a neutron. So here we are, again, we're going to add in our electron, and it's going to not change our atomic mass because, again, protons and neutrons have the same mass, but this will decrease our Z, our number of protons in the nucleus, by 1. So both of these can decrease our atomic number by 1. And again, Z stands for the atomic number, the number of protons in the nucleus, or the nuclear charge. They are all synonymous. Okay. All right. And last, let's talk about balancing nuclear equations. It's actually very easy. We just need to balance both the mass and then we balance the charge. Okay, so in order to balance the mass, I'll highlight it in green. We can look at our mass number to start, and we say that's 238. And then our products must add to 238. So a helium atom with a molecular mass of 4 plus our thorium atom with a molecular mass of 234. Those are going to add together to get 238. Over on my beta decay, I can see the same process here. I have 14 in my atomic number for carbon. I have 14 in my atomic number for my atomic mass for carbon, my atomic mass for nitrogen, and I have 0. So 0 plus 14 equals 14. So that all checks out. Now that's the mass, and I also want to balance my bottom part, which we can consider the atomic number, we could consider it Z, or we consider the charge. Well, 92 is what I start with for uranium. Thorium has 90, helium has 2. You add them together, you get 92, and that is equal. So that checks out. Carbon starts with a atomic number of 6. Nitrogen has an atomic number of 7, and the electron it emitted has an atomic number of -1. So -1 plus 7 equals 6. And that's why I sometimes talk about this in terms of balancing charge, because it's like the charge that balances here. 7 and -1 equals 6. So, but that's how we balance these nuclear equations. So it's very, very similar to balancing any other chemical equation in the sense that you're just looking at the law of conservation of matter. Now, last thing for this video, I want to talk about our radioactive series. So elements do not just simply go from A to B. They do all kinds of fun stuff, right? Here's our little blurb. It says a series of nuclear reactions that begins with an unstable nucleus and results in the formation of a stable nucleus is called a radioactive decay series. And you can see that this reaction shows us uranium-238 decaying into isotope. This is very common. This is what happens on Earth. This takes about 4.5 billion years. This is how we actually measure the age of the Earth. And you can see that my red lines show alpha decay, which should decrease my atomic number by 2. And so I go from uranium to thorium, and so I go from 92 down to 90. Hey, that checks out. Well, then I have beta decay. And beta decay actually increased my charge by 1 by getting rid of a negative charge from a neutron. So 0 minus 0, getting rid of a positive charge here. Sorry. Getting rid of that negative charge is going to leave behind a positive charge. So it's going to increase my atomic number by 1. And then I undergo another beta decay to go back up to the uranium-92, but this one has a mass of 234, which then it's going to undergo alpha decay, alpha decay, alpha decay, alpha decay, alpha decay, to make it all the way down to lead-214, where it will engage in more beta decay, followed by alpha, more beta, more alpha. And I bring this up not to make you do a bunch of these things, but instead to show you how this process can be fairly complex. It's rarely as simple as going from one element to another, and often elements combine multiple types of decay in one process. All right, guys, thank you for listening. That's all I have for this video. I'll see you in the next one.